All right, here we go. Now we can get started. So, maybe. There we go. All right, to begin, we are going to do, I wish this was out of the way. There we go. All right, we are starting with directional derivatives and the gradient. So, we're going to ignore that equation. This is our equation for the gradient in two directions. Essentially, you take your partial of your function with respect to x, and that is your vector component in the I direction. And then you take your partial derivative of y, and that is your component in the y direction. So that's in the I, j, k kind of vector format. Another way of saying this is you have a vector, and it is fx and fy. Then when we want to take our directional derivative, we do the dot product between our gradient and the vector u. And the vector u is just whatever direction we are taking our directional derivative of. And that u vector is a unit vector. So we need to make sure that has a magnitude of 1 whenever we do it. Um, let's see, properties of the gradient. Um, If the gradient is equal to 0, then the directional derivative is 0. If it's not equal to 0, then the directional derivative is maximized when u points in the same direction as our gradient. So if you think about it, when our gradient, because the gradient is a vector of our derivatives, and derivatives tell you your slope or your rate of change. And so the direction of your rate of change is where your rate of change is growing the fastest. And then the last one, if it is not equal to 0, then the directional derivative is minimized when u points in the opposite direction from the gradient, or in other words, when, yeah. So you grow the fastest when you're pointed in the direction of the gradient. You go the slowest when you're pointed the opposite direction. Yes, yes. So steepest ascent is the first one, steepest descent is the second one. All right, so let's do a practice problem. We have a function f of xy is equal to x cubed plus y cubed minus 6xy plus 2. And we are given a vector u pointed in the direction 2I plus 3j. And we want to compute three things. We want to find the gradient, we want to find the directional derivative, and we want to compute the direction of steepest descent at 2, -1. So I'll give you some time to try those on your own based off what we just talked about, and then we'll come together and work on it. Hmm? No. You need a writing utensil too. Okay. And if you have like a not clean like square root or something, don't worry about writing it in decimal form because I'm not going to. Got something? All right, let's walk through it then. So if we want to compute the gradient, all that is all we need to do is find our two partial derivatives. So our partial with respect to x is going to be this first term, derivative with respect to x becomes 3x squared. Y cubed is constant with respect to x, so that goes away. Minus 6xy becomes minus 6y. And 2 is constant, so that goes away. Is that what you got for f of x? Awesome. So then our f sub y, this time the x cubed goes away. We get a 3y squared. And then we have a minus 6x, and the 2 goes away still. That means the gradient of f is a vector 3x squared minus 6y, comma 3y squared minus 6x. Cool? Okay. And then we want to do our directional derivative. So this time we're going to now use this vector 2, 3, and we're going to do it at the point 2, minus 1. So first we have, jumping ahead, we have our vector 2, 3. And is that what we're going to use with our dot product? Nope, we need to make it a unit vector. So in order to do that, we need to find the magnitude, which is square root of 2 squared plus 3 squared, which is 4 plus 9, or square root of 13. So then our u as a unit vector, keep accidentally pressing forward. Oh my goodness, I moved it and it still happened. Wait, where did it go? Okay. Is going to be just our vector u divided by our magnitude. So we're going to have 2 over root 13 and 3 over root 13. Now, we already did our gradient, but this time we want to evaluate it at the point 2 and minus 1. So it was 3x squared minus 6y and 3y squared minus 6x. So now we evaluate that at 2 minus 1, and we get 3 times 2 squared minus 6 times negative 1. So that's 3 times 4 is 12, plus 6 is 18. And 3 times negative 1 squared minus 6 times 2, that's 3 times 1 minus 12, so we get a minus 9. So now all we need to do is we need to do a dot product to find the directional derivative. So it's going to be 18 times the 2 over root 3 and the minus 9 over the 3 root 3. So we're going to have 36 over root 13 plus a minus 27 over root 13. And that leaves us with a 9 over root 13. Awesome. That's the second part. Now we want to calculate the direction of steepest descent. And as we just talked about, the direction of steepest ascent and descent are in the direct same kind of line as our gradient. But since we're wanting the descent, we're just going to multiply it by -1. So steepest descent is going to be the negative gradient of f at our point 2 minus 1. And since on the previous slide, we found that our gradient at that point was 18 minus 9, that just means is going to be minus 18, 9 is the direction of steepest descent. Now, if we wanted to normalize that and turn it into a unit vector, we could, but since all it's asking for is the direction of steepest descent, that's fine. Cool. Any questions about any of those three problems?
I thought it was take the magnitude of the vector and then negative that.
Oh, okay. No, since we're asking for the direction, direction implies it's a vector. Yep. Okay, awesome. All right, absolute and local extrema. So we have critical points whenever our first derivatives are equal to 0. And or when the first derivatives do not exist. And then we can use our second derivative test, just like we did in Calc 1, to find whether it's a local maximum, a local minimum, or in this case, we now also have saddle points. And now instead, since we have multivariates, our second derivative test is no longer just our second derivative, but we have to use multiple second derivatives in order to test it. And we do this thing called D, and it's called D because it's the determinant of a matrix. Oh, I always do that. That's going to become a regular thing if I don't move this out of the way again. Okay, so essentially this D is equal to the determinant of a matrix of our second derivatives. Where we multiply the diagonals by each other and then subtract the multiplication of the off diagonals. And in this case, since we have fxy multiplied by fyx, and as we talked about yesterday, due to Clairaut's theorem, those are equal to each other. It comes out to just be d is equal to fxx fyy minus f, and you could call it either one, but I'll call it xy squared. And then if that is greater than 0 and our double derivative with respect to x is greater than 0, it's a minimum. If our determinant is greater than 0 and our fxx is less than 0, we have a maximum. And if our determinant is less than 0, we have a saddle point. If the determinant is equal to 0, then the test is inconclusive. Then if we have a function defined over a bound and we want to find the absolute critical points, we'd want to test the critical points we found using this with our fx and fy equals 0, but we would also want to test the extremes of that bound. So here's a function of x and y, and it's defined over a domain, and we want to find any critical points as well as what type of critical points they might be, and the absolute extrema. So again, I'll give you some time to try and work on this on your own, and then we'll work on it together. If you need me to go back to the determinant with the greater and less than and all that. Okay, cool.
Function or the first order
partial? The first order partials is what you use to find the critical points.
F of x and then f of y set those equal to 0.
Yes. Yes. Yep. F sub x and f sub y are both equal to 0. What x and y points makes that happen? Mhm. I put in them for you. So it will click through for you. All right. Let's work through it. So in order to find our critical points, we're going to take our first derivatives. So f sub x is equal to, started writing that wrong immediately, 2x minus 2y minus 4. Is that what you got? All right. And we have f sub y is equal to minus 2x plus 8y minus 2. And we're going to set both of these equal to 0. So we can solve this using elimination, substitution, whatever you want. Since I have a 2x and a minus 2x right there, I'm going to go ahead and add them and do elimination. So fx plus fy is equal to minus 2x plus 8y minus 2 equals 0. So when we add both sides, we have a 2x and a minus 2x, which cancel. We have a 6y left over, and a minus 6 equals 0. So now we just need to rearrange this. 6y equals 6, therefore y equals 1. Now we can just plug that into one of our equations. 2x minus 2 times 1 minus 4 equals 0. That's 2x minus 6 equals 0. 2x equals 6. X equals 3. Therefore, our critical point is at 3, 1. And if I go ahead and erase this real quick, maybe, if it wants to. Let's see if it will let me just. Nope. Okay. Because I did it doing substitution as well in the slides, and I wanted to show that off. I did it in substitution when I did the slides, and then looking at it right now, I was like, wait, that's pretty easy with elimination. So with substitution, I went ahead and solved for x as a function of y, and then I substituted it into the f sub y, and I went through and I got y is 1, and I got x equals 3. So got the same thing both ways. Okay, so now we want to do our second derivative test at that 3, 1. So we need to find our second partials. So if we remember, our first partials were 2x minus 2y minus 4. Oh my gosh, what is this? And then we had f sub y was minus 2x plus 8y minus 2. So then when we take our second partials, we get f sub xx, which is 2, f sub xy, which is minus 2, and f sub yy, which is 8. So now we fill this in, and we get that our determinant is equal to 2 times 8 minus 2 squared, which is 16 minus 4, which is 12. And since 12 is greater than 0 and our f sub xx is greater than 0, this is a minimum. Awesome. Now we want to find absolute extrema. So we're going to evaluate the function at our critical point of 3, 1. And we're also going to evaluate it at the bounds. So we're going to do f of 0, 0, f of 4, 0, f of 4, 2, and f of 0, 2. And when we evaluate these, that's kind of just plug and chug. So I don't mind just kind of showing those. We get f of 3, 1 is 17, f of 4, 2 is 20, f of 0, 0 is 24, f of 0, 2 is 36, and f of 4, 0 is 24. So the minimum that we calculated using our critical point is the absolute minimum, and our 0.02 gets us the greatest value, so that's max. Yes, yes. These were just plugging these points into this equation right here. Cool. Any questions about those problems? Cool. All right. Lagrange multipliers. So Lagrange multipliers are helpful for finding maxima and minima, or essentially critical points, with constraints. So if you're given a surface function or just a multivariate function in general, and you're given a constraint function, you can use these to solve those problems. For example, back in like Calc 1, you usually do a problem where it asks you to maximize your backyard area based on a certain amount of fencing perimeter. And you use that using single derivatives, but we could solve that same problem using Lagrange multipliers with multivariate functions. So we're just going to go through and walk through an example with this one. So a golf ball manufacturer has developed a profit model that depends on the number of golf balls sold per month and the number of hours per month advertising. A budgetary constraint function relating the cost of golf balls and advertising is as follows. And so we want to go through and we can want to find essentially the amount of profit that we can develop based on the constraint of how much money we can put into the system. So we have our functions up there. This first function is our how much we make, and the second function is how much we can spend. And so what we're going to do is we're going to create a system of equations by relating the gradient of our budget function to the gradient of our constraint function multiplied by a constant. And we just call that constant lambda for fun. So in order to do this, we need to find our first partial with respect to x and our first partial with respect to y of both functions. So f sub x is going to be 48 minus 2x minus 2y. And g sub x is just going to be 20. Then f sub y is going to be 96 minus 2x minus 18y. And our g sub y is going to be 4. So we can create a system of 3 equations because we relate our partials like this. So we have 48 minus 2x minus 2y is equal to 20 lambda. We have 96 minus 2x minus 18y is equal to 4 lambda. And then we use our constraint function g. So we have 20x plus 4y equals 16, or 216. My bad. So now we can go through and solve this. Let's see, what is the best way to go about solving this? We could express our functions in terms of each other. Let's solve for both of these in terms of lambda so we can set them equal to each other. So for the top one, lambda is going to be 48 over 20 minus 2 over 20x minus 2 over 20y. And that can simplify a little bit. We get 12/5 minus 1/10 x minus 1/10 y. And down here we get y equals 24, or lambda equals 24 minus 1/2 x minus 9/2 y. And now that we've solved both of those equal to lambda, we can set them equal to each other. And I'm going to go ahead and multiply both sides by 10 in order to get rid of our fractions, because I don't like fractions and I'm sure y'all don't like them either. So when we multiply by 10, we get 240 minus 5x minus 45y is equal to 24 minus x minus y. So now I am going to go ahead, and it seems like maybe solving in terms of a function of x in terms of y might be a little bit nicer. So I'm going to subtract 24, add 5x, and add y to both sides. So minus 24, this is going to be a 216. This is going to be a minus 44y, and this is going to be equal to 4x. Therefore, x is equal to minus 11y plus 216 divided by 4, which is 54. Now that we've finally found a function of one of the variables in terms of the other, we can plug this into our constraint equation to solve for y. So we're going to have 20 times our x plus 4y is equal to 216. So when we multiply that 20, we're going to have a minus 220y plus 540 times 2 is 1080 plus 4y equals 216. So then we can combine those. We have a minus 216y equals 216 minus 1080, which is 264, or 864, I mean. So we have minus 864. So y is equal to 864 divided by 216, which I'm going to assume is 4. Yep, it is 4. It looked like it was a multiple of 216. So now all we need to do is take our x equation from earlier and plug in that y value. And we have minus 11 times 4 plus 54. So x is equal to minus 44 plus 54, which means x is equal to 10. So in the context of this problem, that means we wanted to have 10 golf balls and 4 hours of advertising per month in order to optimize the amount of money we'd get with the money are willing to spend on it. Does that make sense? Any questions about that? Cool. Answers 10 and 4, we got them right. All right, double integrals. Back in your pocket. Just clip that.
Double integrals are just like normal integrals, single integrals, but there's two of them. So we're going to do them back to back. Just like how a integral is the area under a curve in a 2D graph. For a three-dimensional graph, it's the area under a curve again, but now it's three-dimensional. So you take that integral by holding one variable constant at a time, either x or y. You hold them as constant, and then you integrate the other variable before switching and integrating the variable that you held constant. So you integrate twice, why they're called double integrals. There's a few properties of double integrals. For just like normal integrals, if you have a sum of two functions, two separate functions, you can split those up and integrate them separately. If you have a constant in a function, that can be brought out to the front. You know, if you have this c, you can pull it out in front. That's what that shows. If you have two separate functions that are multiplied together and the bounds are constant, you can split up the two functions in terms of x and y and integrate them both as single integrals and multiply those together if the bounds are constant. And then here, this just shows Fubini's theorem, which relates the double integral over a rectangular area, AB and CD in the x and y directions. So that just is an easy way to switch the bounds of integration from dy dx to dx dy, in case that's easier. So any questions about that? Spicy. Okay, we'll go and do an example really quick. The double integral of xy minus 3xy squared dy dx in the region from 0, where x is between 0 and 2 and y is between 1 and 2. Go for it. I'll give you a minute. Okay. Well, I'm actually going to solve this in two different ways just to show the different properties of double integrals. The first way, we'll just solve it straight up, or actually, we'll break it up first and then we'll solve it all the way through, just brute force the second way. So we have the double integral. Since we're doing a dy dx here, we have to integrate the y bounds first on the inside. So that's 1 to 2, and then x on the outside, which is 0 to 2 of the function xy minus 3xy. Wow, that's really, it does that, huh? Okay. Okay. Y is squared. Thank you. And we can break this up because there is a minus sign. We can break that into two different integrals, both in terms of x and y. So this would be xy dy dx minus 3, because there's a constant here. We can pull that out in front of our integrals, xy squared dy dx. Now this can actually be broken up even further. Sorry, I didn't write the bounds of integration. I'm lazy. You can break it up further. Remember, if you have a function of x and y multiplied together, you can integrate them separately as long as there are fixed bounds, which in this case there is. It's just a rectangular region, which means this function is equal to the integral from 0 to 2 x dx times the integral from 1 to 2 y dy minus 3 times the integral of from 0 to 2 of x dx times the integral from 1 to 2 y squared dy. Oops, that's an x. Meant to be y. Okay. Excellent. So now we can go through and integrate. The integral of x dx is 1/2 x squared over the bounds from 0 to 2. That is 2 times the integral of y dy, 1/2 y squared over the bounds from 1 to 2 would be 4 minus 1/2. Is that right? 2 minus 1/2, which is 3/2. And then minus 3, same sort of deal over here. These integrals are the same, so that's very handy. 2 times y squared would be 1/3 y cubed. Everyone following these integrals here? Okay, 1/3 y cubed from 1 to 2 would be 8 over 3 minus 1 over 3. Let's make sure we got that right. Vary from 1 to 2, 8 over 3 minus, yes, 1/3. Okay, so that would give us 7/3. Okay, just making sure. Wow, that's really annoying. Okay, so we go back through, we calculate this as 3. These twos cancel. Minus 3 times 14 over 3. These threes cancel. And we get a final answer of 3 minus 14, which is -11. So what you guys got? You got -8? -15. Oh, we're disagreeing here. Okay, this is very exciting. Hey, let's solve it. Solve it another way. We'll just avoid breaking it up and we'll just solve it straight up. We'll see who's right. Okay, bounds 0 to 1 to 2. 0 to 2 of xy minus 3xy squared dy dx. We'll go integrate with respect to y first. We get 1/2 y minus 3 over 3 xy cubed, evaluated from 1 to 2. Okay, so you're correct. Xy squared. For some reason, I didn't write that down. Thank you. Okay, yeah. Xy squared. Pretend that looks pretty. And okay, so we'll go from 1 to 2. We got, that would be a 4 over 2. That'd be 2x. 2x minus 8x minus 1/2 x minus x. Following? Okay, okay. Negative 6x plus 1/2 x is what we come out to, which is 11, negative 11/2 x. Wow. Okay. And we integrate that. That's a very nice function to integrate. Negative 11/2, negative 11/2 x, which would just be, I mean, that's a constant, so we can just integrate without it. But why am I blanking?
Negative 1.
You're right. Negative 11/4 x squared. 0 to 2. Okay. We take it from 0 to 2. 2 times 2 squared is 4. The 4's cancel. We get left with negative 11. Okay. I got the same answer twice. I hope I'm right. Okay. 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 Oh my gosh. Okay. So that means that the function lies below the plane. Just like if you do an integral in the xy plane and the function is below the x-axis, that's like a negative area.
That the time we have a surface,
Mhm.
or have a negative volume underneath.
Right.
Ah,
Good
but
question.
We wanted to know, just like that volume, we can just take the absolute value. Yeah. Yes.
Okay. Spacey. Oh my gosh. Okay. Triple integrals. Very similar to double integrals, just more same rules. You can break them up. You can take constants out of them, or scalars as they're called here. They're separable if you have function of f, a function of x, a function of y, and a function of z. You can break it into 3 integrals, 3 times the fun. And again, there's a Fubini's theorem for 4 dimensions, in terms of the volume AB times CD times EF for the X, Y, and Z bounds. Okay, very similar. We got an example here. Triple integral of x squared yz over this volume. 60 seconds. Hey, spicy. I'm gonna just right off the bat break it into three separate integrals multiplied by each other because we have constant bounds. So we're gonna have the integral of x squared dx from -2 to 1 times the integral of y dy from 0 to 3 times the integral from 1 to 5 of z dz. Okay, so x squared is 1/3 x cubed evaluated from -2 to 1 is 1/3 minus -8/3, which equals 3. Okay. And then we have 1/2, holy cow, this pen. 1/2 y squared evaluated from 0 to 3, which is 9 over 2. Okay. And then we have z from 1/2 z squared evaluated from 1 to 5, which is 25 halves minus 1/2 equals 24 over 2 equals 12. Okay, so those are our partial answers. We multiply them together. 3 times 9 over 2 times 12. And we get, well, so that would be just a 6, right? So 18 times 9, which, can anyone do that in their head? 90 plus 72 is 162. Okay, any questions? Splendid. That's it for, oh, look, we got the right answer, 162. Okay, transformations. Back to Carson.
All right. We're going to talk about transformations, and this idea is used very commonly in Calc 3 with like polar and spherical transformations, in which case you had the transformations. This is polar, it's x equals r cosine and y equals r sine theta. So that was polar. And spherical, oh, and z equals z. And in spherical, x equals rho cosine, no, sine, rho sine phi cosine theta, y equals rho sine phi sine theta, and z equals rho cosine phi. So those are important transformations that are commonly used. But what we're going to use in this example is we're going to do a general transformation. So let's say we're wanting to integrate over a function x minus y, and we have a parallelogram as our bounds, which is shown over here on the left in the image. And those would not be very nice bounds to integrate over. You could probably split it up into multiple integrals in order to solve that, but that would be kind of gross and we don't want to. So what we're going to do instead is we're going to use a transformation to turn this parallelogram into a square and a different unit. And then that way, this integration will be a little bit easier. So the transformations we're going to use is we're going to use u equals x minus y and v equals x minus 3y. And so first thing we're going to want to do is we're going to want to transform each of our coordinate positions from x and y to see what they would be in u and v. So u of, let's start at the bottom left, 1, 2 would be 1 minus 2, so that's minus 1. U of 3, 4 would be 3 minus 4, which is also minus 1. U of 4, 3 is 4 minus 3, so that's 1. And u of 6, 5 is 6 minus 5, which is also 1. V of 1, 2 is 1 minus 6, so that's minus 5. V of 3, 4 is 3 minus 12, so that's minus 8. V of 4, 3 is 4 minus 9, which is minus 5. And V of 6, 5 is 6 minus 15, which is 8. Okay, did I do that? Was that? Because that's 3 minus 12 is, yeah, minus 9. There we go. So we can already see these transformations were chosen really well because our U has bounds of -1 and 1, and our V has bounds of -9 and -5. So now if we were to plot this in the UV plane, that vertical axis is V, we'd have -9 and -5 and -1 and 1. So we'd now have a rectangular region that looks kind of like that, which is a lot easier to integrate than whatever we have going on right here. So we said our bounds were -1 for U and -5 and 9 for, that's wrong, that's backwards, -9 and -5 for V. Additionally, the function we're integrating over is x minus y, so we can just substitute that for a U. Now, normally, cool, that's fine. However, when we changed from this parallelogram into this rectangular form, there's a change in the area of that we need to account for. And so that change we account for is called the Jacobian. And we need to multiply that inside of our integrals in order to get the right answer. So in order to calculate our Jacobian, we're going to take the partials of our transformation functions. So if we take the partial of u with respect to x, we get 1. Take the partial of u with respect to y, we get -1. Partial of v with respect to x, we get 1. And partial of v with respect to y, we get -3. And how we want to calculate that Jacobian is we create a matrix where we essentially have these partials or these coefficients of our x and y. Times our x and y equal u and v. And we want to take the, technically that's not right, but that just works out in this case because it's linear. But really, okay, let me rewrite this. Let me explain this better. Our Jacobian is a determinant of the matrix of our mixed partials. And so since we took our partials with respect to u and v, is going to look like this, where we have the functions right there and the variables there in terms of as the columns. So then we take the determinant, which is going to be du dx times dv dy minus du dy times dv dx. So we're going to have 1 times -3 minus -1 times 1, which results in -2. But it's important to note these are our functions of u and v in terms of x and y. So this is what we would multiply by if we were going from u and v to x and y. But because we're doing the opposite, we're going from x and y to u and v, we actually need to take the reciprocal of this. So our Jacobian is going to be the absolute value of -2 inverted, or 1/2. Does that make sense? If we, and I'll show in a second on this slide, what they do instead is they convert the equations into x and y as functions of u and v, and they find the Jacobian that way, and you also get 1/2 doing it that way. But if you just want to keep it in u and v without turning it into functions x and y of u and v, you just need to do it the exact same way and then find the reciprocal of it. Cool? Any questions about that? All right, so now we can finally integrate this. So we're going to integrate from -1 to 1 and -9 to -5 of u times 1/2 dv du. So now it's just a regular double integral. When we integrate with respect to v, we have a 1/2 uv from -9 to -5 du. And when we evaluate that, we have a -5/2 u minus, I forgot the u, minus a -9/2 u, which simplifies down, that becomes a plus 9/2. 9/2 minus 5/2 is 4/2, which is 2. So we just end up with a 2u du. Now when we integrate, we just end up with a u squared minus 1 to 1. So we get 1 minus 1, 0. Yes, a little anticlimactic, but the answer we got was 0. Does that make sense? Any questions about that?
Transformation given, correct? Like the
Yes. If it's polar or spherical, you might be expected to just know those. And for polar, your Jacobian is always r. And for spherical, your Jacobian is always r squared sine phi. Yeah. And you could prove those doing the same method that we did here. But you don't have to if you can just remember them. So the reason I did that in this one was because our functions were u and v in terms of x and y.
oh, okay, so that's why on the bottom.
Yes. Yes, exactly. And so here I'll go through and I'll erase all this nice work. And I will show, because the slide does it differently. The slide converts it into x and y, and then they calculate the Jacobian, and they will also get 1/2 as their Jacobian. I want to see if that's enough. No, it was up there. Okay. Sorry, give me a moment. This is like the last topic, so once we're through with this, we're done. My goodness, this eraser sucks.
No way to make it bigger.
Nope, it's literally the back of the pen that you write with, like a regular pencil, and it is just janky. Okay. So see up here, I'll move my name. They converted the functions into y and x as functions of u and v. Then in order to find the Jacobian, this time they did, it was del x, del u, del x, del v, del y, del u, and del y, del v. And when you do that with these, you get del x, del u is 3/2. Del x, del v is -1/2. Del y, del u is 1/2. and del y, del v is minus 1/2. So when you calculate that, you get minus 3/4 minus a negative 1/4, which is minus 2/2 or 2/4, which is minus 1/2. And then you take the absolute value always of your Jacobian, and we get 1/2. So see, you could also do it that way and convert it into x and y as functions of u and v in order to find your Jacobian. However, if you just keep it and do it that way, so long as you take the reciprocal, you're good. Exactly. Cool. Makes sense? And then they went through, oh, they got an answer of 2. Did I? Let's see. 1/2 u is 1/4 1 squared minus. No, that should be a 0, shouldn't it?
1/2 u squared.
Yeah. Yeah, but then when we evaluate the bounds, we have 1 squared minus a negative 1 squared. 1 squared is 1, negative 1 squared is 1. So then we have 1 minus 1. I'm pretty sure the slides are wrong. But anyway, that's it. Scan this, leave us feedback. We'll have more reviews at the end of the semester to help prepare you for finals. But yeah, thanks for coming. Appreciate it.